Recording in progress.
Yeah, let's start off with this. Hands on everyone. There, we got a vessel there which is going horizontally also and which is also has a gravity. Find the pressure difference between A and B. This is a good one. Standard model done in the notes also before. Second thing, we have a spherical shell which is accelerating horizontally and there's also gravity. There are 8 points. Arrange the pressures in the descending order. मेरे channel. The first one would be a pretty good mains level question. Hmm. This is a concept of, we have to use G effective, but look at this one. Principal superposition, basically. Imagine only if you're accelerating, then the pseudo force, right, will be acting backward, MA. So if I take point C here, so when you're going from A to C, it feels as if the gravity is A. That is how the system will behave when you go from A to C. So PC minus PA will be rho G. In place of G, you have A, and H ka place mein you have L. Then when you come down from C to B, you can do that actually. You can just travel in the direction of the gravity. So when you're traveling from C to B, then PB minus PC will be rho GB. Add them up. We get PB minus PA will be rho AL plus rho GB. Clear with that? So you just travel in the direction of the gravity, because when you're traveling horizontally, in the horizontal direction, gravity will not affect. In the vertical direction, A will not affect. Right? And the system does not know the difference between gravity and pseudo force. Mathematically, mg and ma, right, other than calling it a and g, there's no difference between them. Same thing I can do here. So here the pseudo force ma will act backward, your gravity mg will act downward. So the resultant force here, a is equal to g, that will be 45 degrees. This is the direction of f net, which will be m into root over a square plus g square, right? So this will be equal to m into g effective. So basically this is down. So what is up and down? The direction of net force is down. You're getting it? So that is the meaning of up and down. And you keep saying up and down, it's not always this is up and this is down. It's the direction of the net force. Then what is horizontal then? The horizontal will be the line perpendicular to this guy. So these lines will be horizontal lines. And we know along a horizontal line, the pressure will remain same. In the direction of the net force, the pressure will decrease. These are horizontal lines. So who is the deepest point here? 6. So 6 will be the greatest. Then P7 and P5 will be equal. Then 8 and 4 will be equal. Then 1 and 3. Then P2. They can even ask you this thing. Find the maximum, difference in pressure. So the maximum difference in pressure will be P6 minus P2 That will be density G effective. In this case, it is G root 2 into the distance 2r. That will be the maximum difference in pressure between 6 and 0.2. Clear with this? If the container was not accelerating, then it is 1 and 5. If it is accelerating with A is equal to G, then it will become 2 and 6. Yeah, all are 45 degrees. Clear? Not a tough one, but it's a good one. So the concept of G effective, quite useful. The same thing again, G effective you'll use in SHM. You can also use it in electrostatics. You can use it in fluids. You can use it in loss of motion. Multiple places this thing will pop up. So be careful with that G effective thing. This guy. We have a U-shaped container. On the left hand side we have a 2-row liquid. On the right hand side we have row liquid. The lengths are same. And the heights are also same. This will happen only if you're accelerating. Normally this wouldn't have happened. Find the acceleration of the container. Second thing, two different liquids, the green one and the red one. You can see how it is. They're in equal volume and they're in equilibrium. Find rho 1 by rho 2. The first one, it's a closed container. The first one, this was a closed container. It's completely sealed. ऊपर कुछ है ही नहीं open. Try. The first one, first and the second one involves little working though. Normally, if you see, the red one should have been higher than the black one if there was no acceleration. By 3. And that looks right, Navya. Right, Ahana. So how do we handle this? Since it is an equilibrium here, let's take this point as A and take this point as B. So if you draw the FBD of this horizontal part, from this side we have pressure PA into area. From this side you have pressure PB into area, and this whole setup is accelerating. So PA into area minus PB into area is equal to mass into acceleration, which is rho 2 rho A L plus rho A L into acceleration. But I know PB is nothing but PA will be P naught plus 2 rho GH. PB will be P naught plus rho GH. A will cancel on both the sides. That will become 3 rho LA. P naught will cancel. We end up with acceleration is equal to rho GH G by 3. Clear that? What about the second one? Second one, I don't think numbers will be that great, but try. I'll give you a minute. These are good ones. Like, these will be the kind of questions you can expect. They will not be too easy, and it's not like they're really out of the world. And when you get comfortable with these level of questions, then comes the next level advanced questions. These will be the building blocks. So don't see the paper QS and think that paper will be easy and everything. Always assume the paper is going to be tough and go prepare with that mindset. So here the idea is the pressure always depends only on the vertical height. It doesn't matter like how is the shape. So that means when you take the height, again same thing here. I will choose 2 points here. Let's call this thing A and this point B. Since the system is in equilibrium at that interface, PA is equal to PB. The 2 points are touching and they're just almost there. Now when you take the vertical height, so if this is 30, this is 60, and this is 30. So this height will be how much? R sine 30. This height will be R sine 60. This height will be, so that's R cos 30, and that piece will be R into 1 minus cos 30. And this height will be, again, that will be R minus R cos 60. Got the heights? Then you're done. So PA will be rho G R 1 minus cos 60, rho 1. This side it will be rho 2 G. The total height will be R sine 30, R sine 60, plus then the liquid changed rho 1 into G R 1 minus cos 30. Then you can simplify this. You will get rho 1 by rho 2 from here. I will leave it to you. Are you clear with this? It doesn't matter what is the shape of the container that I give you. All you're interested is the vertical heights. So when you say rho G H, H is the depth or the height in the direction of net force. Clear with this? Same thing in this, if you remember, there is one more type. We have a U-shaped container. This is rotating with omega. Let's say this is L by 3 and this is 2L by 3. This is another important model. So here the liquids will be, this will be H2 and this will be H1. Right? Find H2 minus H1. You took a U-shaped tube and you're not rotating about the center, but L by 3, sir. Hope everyone has gone through the class notes. See, that's what I keep saying, you didn't get time, you couldn't do, that's completely fine. Do it next. You still have one more class, finish off before that. Or the notes is too big and you are not able to do everything. That's fine. At least finish off half of it. And then remember, I finished only half. So, and then later on, when you get time, you will get time. You do it then. I know there'll be a lot of work to do. The point is that don't get overwhelmed and try to do as much as you can. First of all, you should know when you're rotating what is the formula. That formula itself will be a question, huh? What was the formula there? We have a cylinder here rotating with omega. Just to give you an idea here, there are actually few models like this rotating thing. So if it is rotating like this at a distance x, right? So guys, remember what is the pressure here? Px minus p axis will be rho omega square x square by 2. Remember, this will be the pressure difference between the axis and this thing. Clear with this? That's between always the axis and so axis में pressure we don't know, getting it? So it could be an open container or something. This is one. Suppose same thing, if you have a rod, the rod is rotating with omega and there is a magnetic field. You guys remember the potential difference? क्या था formula? Potential difference of this thing. EMF induced across the rod.
E
So if
omega
I take
square
this,
L by 2.
you have to
E,
type in the chat box, Yashil. We
so
want others
yeah,
also to try, right? Yeah.
yeah, so my bad.
So be careful with the sign also. I hope you guys remember how to take the sign. Assume a plus Q charge, then it's going with velocity v. So QV cross B, see which way it is traveling. So force is this way. So this is actually V0 minus VA. So here O has higher potential. B omega L square by 2. याद आया? We have a rod here. Rod is rotating with omega, right? And the same thing. Find the tension at a distance x. ये circular motion का question था. Mass m, length l. Anyone remember what is the tension at a distance x? This will be important because I can ask you this in circular motion. I can also ask this thing in elasticity. There I'll ask you find the total elongation of the rod when you're rotating horizontally. Neglect gravity. So like that, I can ask in EMI, I can ask in fluid, I can ask in circular motion or elasticity. Anyone remembers if a rod is rotating with omega, mass m and length l, find the tension at a distance x from the axis. You want to derive? Try. I'll give you 30-40 seconds. नहीं बोल रहा. Ask yourself, where will the tension be maximum? Here tension will be maximum on the axis. So if you put x0, you can't get zero tension, you should get maximum. Tension will be zero on the open ends. Free ends will have zero tension. नहीं रहा ना, same thing I'm saying. If you put x0, you should not get zero. In case you forgot, it is circular motion. Here, this is the question. Say, we got a rod here, it is rotating in a horizontal circle, find the tension at. So this is how we did, if you remember. We take a thin slice dx, then we write the tensions, and then we integrate the whole stuff, and that's your answer. Are you getting the limits right? Will not go from 0 to x. Limits will go from L to x. That is a mistake you guys must be doing it. Because if you put 0 to x, you don't know the tension at 0. But the free ends will have zero tension because there's nothing holding there. Right? So that will be important, right? As I can frame it in elasticity. So here tension will be m omega square L square minus x square by 12. Clear with that? Or in case you don't remember, it doesn't strike, there is a faster way to do. You want tension here, right? Take only this piece, assume all the force is at the center of mass at the center of mass of that piece, right? So this centrifugal force must be equal to this tension. You can do that, it works. But you need to take the center mass of that part. So, and that particle length will be L minus x, na? So this length will be L minus x by 2. So centrifugal force will be m omega square r, where m is the mass of the shaded part and r is the radius from the center of mass to the axis. In case you don't want to do integration, you can use that. It works. Because it is m omega square x, na? It's a linear function. Center of mass concept works. Clear with this? So you can play around like this. So the rotating thing, this is what I was saying. When you're doing questions, now don't think only about this. If you can try to connect the stuff to as many chapters as possible, it becomes easy to remember. Your brain will have more anchoring points. Getting it? That is how you actually improve the memory. Instead of telling you to remember something, if I tell you a story around it, you'll actually remember it because your brain has more anchoring points. So now getting back to the question. So how do we do this thing? So we treat this thing as two cylinders. Let's take this as A. This is your axis. This is B. So PA minus P axis will be rho omega square L by 3 whole square by 2. PB. So you cannot write this directly from A to B. Remember that, okay? It has to be written always from the axis only. Rho omega square 2L by 3 whole square by 2. Then we have PB minus PA. And PB minus PA will be rho G H2. Solve this, you'll get the answer. Clear with this? Not difficult, but you should know your formulas. Any doubts on this? Get this thing. We have a container open top. This time on the top it is open. It is filled with 2L by 3. Acceleration is g root 3. Find the volume of the liquid that spills out. B equation, if you remember in the class notes, we did even a much better problem. We said find H1 and H2. That would become an advanced problem, right? But for now, let's just find the difference in height, H2 minus H1. You should check out the notes, how we did for H1 and H2. You guys remember volume of a paraboloid? There is a result. What volume of a paraboloid is? Right, Poraja. Right. No, yeah, most of you guys do remember. Half of the volume of the cylinder it encloses. Meaning, if this is your paraboloid, if you make a cylinder like this, right? So the volume of this paraboloid will be half of the cylinder ka volume. Basically, it occupies half of the volume of that cylinder. So that was a final result. But you should check out, fluid mechanics. I think that was the first or second question. Check out the notes. That would be a good one. So let's get these two. Find the volume of the liquid spilled and find H2 minus H1. Mains they won't ask that. That requires a lot of work. Actually, that could be still a decent paragraph question. That is a really good question. Find omega so that the liquid spills out. Find omega so that the bottom floor gets exposed. You can play around a lot of questions like that. So first one, what happens? Hope you guys remember that result. That's the straightforward result. So the liquid will make actually a shape where tan theta is equal to A by G. Should remember this. In this case, it will be root 3 or theta is equal to 60 degrees. So in this cube, how will you get 60 degrees? So the liquid has to be like this. The actually container ka bottom is exposed. Because if you draw exactly to the corner, you'll get 45, isn't it? And if you want to get 60 degrees, you can't change the height of the triangle anymore. You have to change the base only. So it actually looks like a trapezium here where the bottom is exposed. This angle will be 60 degrees. Clear with this. So once you exceed A is equal to G, the liquid will actually start receding. This bottom part here will get exposed. This will be L, this will be L, and this will be L by root 3. So that's like a trapezium there. So the final volume will be half into base into height into that thing L by root 3. V initial will be L into 2L by 3. The volume spilled will be the change in volume. That is one thing you have to be careful. Most people don't understand how to put that 60 degrees exactly. If you're anything less than 45, the shape would have looked like this. The shape would look like this. So there'll be height on both the sides. Exactly 45, you'll be go to the corner. Anything greater than 45, you'll become like this. This will be 2L cubed by 3 minus L cubed by 2 root 3. Clear with that? The second one, the rotating thing. If you remember, if you take that curve there, if you choose a point, let's take this as origin 0, comma 0, and this is x, comma y. So this particle here is going in a circle. It will experience a centrifugal force dm omega square x, and it will also experience dmg. This was the initial definition of fluid. In a fluid, there's a property. The net force is always perpendicular to the surface. Remember? A fluid is a substance which cannot withstand shearing stress. So therefore, the net force will be always perpendicular to it. So this is a F net. Meaning this will be the tangent. So if you take this angle to be theta, that will be theta, this will be theta. We get tan theta is equal to omega square x by g. But I know tan theta is dy by dx. Integrate on both sides. Y is equal to omega square x square by 2g. That's your equation actually. It's a parabolic thing. Clear with this? So you want the difference in height. So here y will become h2 minus h1. And this will become omega square r square by 2g. But that's your equation of the paraboloid. Any doubt on this? Standard equation. It's a good one. This one. I mixed up 3 different questions here. If you see again, this is the fluid mechanics equation. A liquid, water jet is hitting the wall at an angle theta, E is equal to 1. Light beam is hitting a mirror, intensity I. Find the pressure on the wall. The third question, if there is a mesh, right? If there is a mesh, 40% passes through, 20% reflects, and 40% hits and stops. Then find the force on the mesh. The C is the actual question, though A and B is just to see whether you remember the result. So instead of a proper plate, you made a mesh. 40% passes through, 20% reflects, and 40% hits and stops. Then what is the force on the mesh? The water jet is coming along the normal only. So The pressure ka results are important. So one is from modern physics, one is here. So two different chapters again. The results will be similar. Don't remember the results. Let's see. So if you look at the pressure on the wall due to the water jet, it is rho a square v square 2 e is equal to 1, right? Okay, 2 rho v square cos square theta. For the light beam, the pressure will be 2I by c cos square theta. If they ask you force on the wall, then it will be 2 rho a v square cos theta. There will be one cos theta for force, because if you guys remember, pressure will be forced by area. Area is what? The area where the water jet hits, and the area will be actually quite bigger. So this is 2I by c a cos theta. So in this case, just to make you remember, this is force, and in this scenario, the area is actually a by cos theta. We have a very good discussion on this in fluid mechanics and modern physics also. Should check it out. But the first time we encountered this was in fluids, and recently we saw this in modern physics. Clear with this? So A is not the area of the water jet. A is the area where the water jet hits the, the surface, and you can clearly see the water jet actually spreads out. This is area A. When it hits here, it is actually hitting this area, which is A by cos theta. So now coming back to this question, so what is the answer? If it passes through, then the force will be 0. If 20% reflects, you can assume as if it's a 0.2 thing. So 2 rho A V square into 0.2. 40% hits and stops. So if it just hits and stops, rho A V square into 0.4. Clear? Add them up, you will get the answer. That's 0.4, 0.4, 0.8 rho A V square. Clear with this thing. So you can just treat it as, a water jet of 0.2 times is hitting a wall, 0.4 is passing through, and 0.4 is hitting and stopping. Now, same thing, if you continue with the pressure, if you have a soap bubble, charged soap bubble, sigma is the charge density, S is the surface tension. Find the pressure inside. Uniformly charged solid sphere. Find the pressure inside. Current carrying hollow cylinder. Find the magnetic pressure. Current carrying solid cylinder. Find the magnetic pressure. So if you see this pressure ka term in total, right, it comes in how many chapters? Fluid mechanics mein fluid ka pressure, right? And then we get it in electrostatics as electrostatic field pressure. Then we get in magnetism as magnetic field pressure. And then you also get it in modern physics as radiation pressure. So in total, you will hear the word pressure 4 times. And mathematically, right, the formula might be different, but the way it behaves, right, Max doesn't care what kind of pressure it is, forces pressure into area. So things will look same. Let's see whether you remember this result. First one, you should definitely try to do. That's a pretty good question. Remember, excess pressure in a soap bubble. But this time I kept a charge on top of it. So find the pressure inside the soap bubble. And let's see, remaining 3, you remember the results. Hmm. How would be the first one? What's the formula there? If you guys remember the excess pressure inside, first of all, do you guys remember these formulas? There, these are the formulas. Actually, I'll give it to you. If you have a conductor, okay, this is for conductors, okay, of any random shape, then the pressure on the surface is given by sigma square by 2 epsilon. It's easy to remember. It's your basically, energy density only. The energy density term will come like pressure sigma square 2 epsilon or half epsilon E naught square on the surface. But if you take a spherical shell, even if it's a non-conductor, the formula still works. You're getting it. For conductors, independent of shape, the pressure is always, sigma square by 2 epsilon. But for spherical shells, conductor or non-conductor, the pressure is sigma square by 2 epsilon. So what will happen to the pressure inside? Normally, if there is no charge, what is the pressure? P naught plus 4s by r. Because of the charge, the shell is trying to expand outside, so pressure will drop minus sigma square by 2 epsilon. Clear with this? So they can ask a question like this: find the charge on the shell, the soap bubble when it pops. When does it pop? When the pressure becomes equal to outside pressure. So if sigma square by 2 epsilon and 4s by r become equal, the shell will pop. Meaning the soap bubble will pop. Clear with this? For the solid sphere, this is the formula. Rho square by 6 epsilon r square minus x square. The same formula, you can also use it for gravitation. Isn't it? So gravitational field pressure. So that is actually the fifth one. So gravitation, electrostatics, the results will look similar. How do you get results of gravitation from electrostatics? Rho is the charge density. Gravitation में rho is the mass density. What happens to epsilon? If you remember, K is G, right? So 1 by 4 pi epsilon is G. So wherever you see 1 by epsilon, you can replace this with 4 pi G. Clear with that? So replace 1 by epsilon with 4 pi G and you'll get your answers. It becomes gravitational field pressure. And this is your pressure on the surface and this is the pressure inside. So this we have done it in magnetism. You should check out that. This is electrostatics and that's magnetism. Electrostatics and gravitation. So total there are 5 pressures actually, including gravity. Yeah, but mostly this will enter into the advanced territory. But I think till here this is still decent. The right side, the three things will be mostly advanced only. But you should know the field due to the shell there. Do you guys remember this result? If you have a perfectly absorbing or a perfectly reflecting, the force will remain same. We have done this in the modern physics. So that's so based on radiation pressure. Can you get this question? You have a thin shell of radius r and thickness t. B is the breaking stress. Find the maximum sigma, the surface density on the shell, so that it does not break. If you keep putting a lot of charge on the shell, what will happen? Eventually, the shell will pop. Find the maximum surface density on the shell so that it does not crack. So electrostatics and elasticity and fluid mechanics. Total 3 concepts are involved here. And you should definitely look at the notes. Once in the pressure, we have a concept of projected area. Very important concept. Literally comes in 6 to 7 times. And you should definitely go through that one. Saves you a lot of time. It comes in projected area concept, comes in fluid mechanics, surface tension, electrostatics, Gauss law, right? Magnetism, modern physics. Meaning it just pops up everywhere. So it's quite an important thing. EMI. It comes in EMI also. Do you guys remember that? Projected length. If a weird shaped rod is traveling, you just take the distances between the two ends. BLV, where L is the projected length. So the projected area and projected length concept is very important. So definitely make sure to go through that. They should especially target these kind of things, where it will pop up at least more than, one time or 2 times. Then you'll actually cover much, a lot, and you'll remember much better. So don't try to see in physics, don't try to see chapters as independent. You see, even though I'm saying fluid, literally everything is coming up from everywhere. How to do this? Let's see. So take an half shell. So on this area, which is, this is your tension. Okay, and the field pressure will be how much? This will be pressure into projected area. In case you forgot what's the projected area, sure. So if you have any random surface, so the force on that curved surface will be equal to, you just take this area. So projected area will define this thing, an area which makes an open surface into a closed surface. So if you want to make this random surface into a closed surface, I just need to fill up this disk. So this disk will be the projected area. And the proof is pretty simple. The net force acting on the system, if it is a closed surface, the total force is 0. That means force on the curve plus force on the flat disk must be 0. So therefore force on the curve must be force on the disk. But this will work only when the pressure is constant. If the pressure is not constant, you are gone. You have to integrate. You can't do this thing. And then we had few examples. Especially this half cone is a very good example. Look at this half cone example once. If you take an half cone, there are 2 projected areas. Remember, you have to make it a completely closed figure. So you have one triangle and one half disk. So find the force on the triangle and the half disk. That will be the force on this half cone. Clear this thing? So projected area is that area when you put it back, it becomes a completely closed figure. So here our projected area will be this pi r square thing here, this green shaded thing. What's the pressure? Sigma square by 2 epsilon. And what is the area? Pi r square. From here you got the tension. What is the breaking stress? Breaking stress B is nothing but tension by area where the tension is acting. Where is the tension acting? It is acting on the thin cross section there, which is tension by circumference 2 pi r into thickness T. Are you clear with that? So substitute there and you'll get sigma value from here. So be careful. There are 2 different areas here. When you're taking for pressure, it is area of cross section, this area in the middle. But when you're taking for the stress, you are taking this thin strip, the 2 pi r into T. Both the areas are different. Are you clear with that? So be careful with that. Let's get this. This is a good one. Thermal expansion. So we have a container filled with liquid, rho and R and H. If this was a mains question, I'll ask you this. If the temperature increases, what happens to the pressure at the bottom? It will increase, it will decrease, it will remain same, or it depends on the value of alpha, it will depend on rho. I will pop up 3-4 questions. That would be a pretty good mains level question. If I increase the temperature, what happens to the pressure? Increase, decrease, remain same, or it depends on the values of the rho, alpha, and gamma. It's a 4 options over. I'm here to literally asking you find the change in pressure, so I give you all the data though. Let's get this. Last time speed test ka highest was I think the way he did around 75 questions attempted and he got around 72 right. Let's see today what will happen. Not today, but I think next week or something. I'll keep a test only on semiconductors, magnetism, all those main topics ka speed test. That would be fun. Nah, I'm sure another 1 or 2 tests, you guys will start hitting 70 plus, most of you. Don't worry. You'll get used to it. So what is the answer for this guy? I'm forgetting. Wait, last class का वो question था ना? I was reading that question only wrong. Where was that? This one. This one. I was trying to find the figure of merit. The question was find the current. It clicked to me later. So listen to this thing also. I'm forgetting this. Let me teach you right now. So what he is giving you, right? He's asking you to find capital I. So what is capital I? Capital I is Ig into 1 plus resistance of the galvanometer, which is G by shunt resistance. Figure of merit is I by theta. So basically it is current per unit division, which is figure of merit is what? K. This is spring constant. We'll get confused between this K again. So figure of merit is simply current per unit division. Which is in this case Ig by N. So take Ig and substitute here. So that will be N into K. This will be G plus S by S. Plus A tha. So D was the answer. I was finding figure of merit. I was thinking, what the hell? Anyway, current was easy. That was. So be careful. Mostly in that question, the scary part was that only figure of merit. Most people don't remember what is figure of merit. If you know that question is easy to solve. That was one last thing we had a pending. So what is the answer for this? It will always increase. Increase, no, decrease. The simplest way to figure out is this. Tell me one thing. What is pressure on the base? Force by area. What is the force? Mg. If you increase the temperature, decrease the temperature, will Mg change? Mg will not change. But when you increase the temperature, base area will become bigger. So you're putting the same amount of weight on a bigger area. So what happens to the pressure? Decreases. Clear with that? So if you increase the temperature, pressure will decrease. Done. Matlab, it doesn't depend on rho, gamma, and all that. It will always decrease if you increase the temperature, independent of values of rho and gamma and all that stuff. But let's calculate. So most people, right, they try to do in terms of H and all. That becomes confusing. Don't do that. If you see in terms of mass, your life will be easy because m will not change with temperature. And how will the height change and all? We will see that in thermal expansion. So area becomes A into 1 plus 2 alpha delta T. So initial pressure mg by area, P final mg by area into 1 plus 2 alpha delta T. Right, and mg is nothing but a rho into A into H into G. That's basically rho GH. So this will be rho GH by 1 plus 2 alpha delta T. That you can subtract them, you'll get the change in pressure. Easy. This is what I was saying. If you actually understood what to do, right, these questions won't take more than a minute. But these are not easy also. I won't say they're easy. You need to think. But then they won't take much time to solve if you're actually thinking in a proper way. Let's get these two. Hope you guys remember. A is a standard model. We have a square plate of Seidel. Left side, there is a liquid of density rho. At a height h from the top, someone is applying a force F to keep in equilibrium. When I say equilibrium, translation and rotation, both the equilibriums. That's a standard result actually, but let's see. Second is a good one. If you keep an half disk inside the liquid at a depth R, find the force on one surface. On both the surfaces, it will cancel out. Find the force due to the liquid on one surface of the disk. Now, if you know the result, it looks easy. So B looks like a monster. But let's get the first part. Density changes in the final pressure. Oh God, mg doesn't change, right? I am not putting density. I am putting m ka value, na? Navya. M ka value is always what? Initial mass only. What is initial mass? Rho AH. In case you're still worried, I'll show you why. See. Density becomes rho into 1 plus gamma delta T. Volume becomes 1 plus gamma delta T. Na? This will always cancel. Density drops, volume increases, so net mass will remain same. How to do these two? If you just want force, life is easy. You just take the center mass and finish it off. But if you want torque, life is not easy. You have to integrate. Or if they really want to mess up, they will do something like this. They will say density rho is equal to rho naught y, where y is the depth. So then you should know still how to integrate the stuff. So let me show you. So at a depth x from the top, take a thin slice dx. So on this, the liquid will be pushing with some df. So df will be left side and right side, p naught will cancel. So I'm ignoring that. So df will be rho g x, that is the pressure, into area will be, if I take this length to be L into dx. It's a square plate. So you want the net force, that would be integral rho g L x dx from 0 to L. That will come out to be rho g L square by 2. That is the force which should be applied. What about the torque? the torque due to the small df will be x into df. So the total torque will be rho g x L dx into x from 0 to L. This will be rho g L L cubed by 3. This must be equal to the force which is applied F into H. And if you substitute F there, H is equal to 2L by 3. So you should apply this much force at a depth of 2L by 3 so that the plate won't rotate and plate won't translate. You cannot apply in the center. I clear with this. There are two things here. So this is the force for equilibrium translation. But where should you apply this? If you apply wherever you want, the plate will start rotating, isn't it? The plate can become like this. It won't remain vertical. So torque also must be 0. So the torque due to the liquid must be equal to the torque due to the force F. And logically be socho na, where is the torque more? You can clearly see the pressure at the bottom is more. So shouldn't the force be more below the center of mass? But this is a standard result kind of thing. But I want you to know the derivation because you won't be so lucky in the exam. They will say rho is equal to rho naught x, where x is the depth. Not difficult to solve. If you know how to take an element, you'll just add up one more x there. What about the B part? B is a good question. There is a result we derived here. So force on a surface is pressure at center of mass. That your center of mass is also there into projected area. We have proved this in detail. If you can check out the notes. It is the same question. I gave it as H though. So I took a small element and everything, and we proved actually right that this value turns out to be center of mass. So you can see 4r by 3 pi. So this is a general result, okay? If you take a sheet, this is only for sheets. If you take a sheet and dip it in a liquid, the force on one side of the sheet will be the pressure at center of mass into area of the sheet. This will work when the pressure is constant or changes linearly. If you put pressure is x square, this is gone. You can't use this. Then you have to integrate again. It's a pretty neat result. So if you remember that, then you're done. Basically, where is the center of mass? Center of mass will be here at a distance of 4r by 3 pi. You should know your center of mass result. So that means from the top, what is the pressure? P naught plus rho g r plus r minus 4r by 3 pi. That's the pressure at the center of mass, and the area of the disk is pi r by square root. You can't take torque about the center, right? How are you taking torque about the center, bud? If you take torque about the center, this is pushing this way, this is pushing this way. Directions are opposite. Did you subtract them?
Yes, sir.
You didn't subtract. You added them all.
No, I subtract.
Then ठीक है ना? You got L by 6 from here. So I took L from the top ना. So you got 2L by 3 only.
हाँ शायद वही.
So you got the same answer though. Are you clear with this thing? This thing looks easy, but that is because you know the result. Or else you have to derive here. How will you take elements here? You have to take strips like this and then you have to integrate the whole thing. That would be actually a little work. But it's a pretty good result though. Clear with this? This though I showed you. This is another good one. Let's get this. This time there's a surface tension also. This we did, so I'll not do this again. So we have a U-shaped container, but this time the radius is R1 and R2. They don't have same radius and surface tension is given. Contact angle is 0, find H1 minus H2. Second thing, we have a U-shaped container, liquid is total 4L, find the time period for small oscillations. For which one, Ray? Issue? For the torque thing you're saying?
Yes.
Actually, see, if a system is in rotational equilibrium, then torque over at any point is 0. But we will take from the top because when you measure pressure net is rho gx, where x is the depth from the top. So I would prefer to take it from there. So if you take from any other point, you have to take care of that. Let's get this thing. Now, if you ignore the surface tension, we know H1 is equal to H2. But if you have surface tension, they won't be same. How do you include that? The second thing is a find time period for small oscillations. Second part, I didn't give you surface tension. I don't include. How do you know whether you have to use surface tension or not? Check whether they're giving surface tension ka value. See, there is an easy way to guess the first one, okay? If there was no surface tension, H1 is equal to H2. Now, because of the capillary action, the left side will try to go higher, which is how much? Remember, H is equal to 2s cos theta by rho g R1. The right side will try to go 2s cos theta by rho g R2. Subtract them, you're done. You'll get the answer that way. Getting it? Because of that extra surface tension, you will go this much height. Right? But if you want to solve this is how you do this. And listen, this is important. There is an important concept there. This is there also HSC 12th standard ka board ka derivation. So they'll ask you find the height of a capillary action using pressure method. Do you remember I taught you two methods? So when you take this capillary, and when the liquid goes up here, now if I exaggerate this figure, so this is not exactly a perfect circle. So it will be something of this sort, and the center will be somewhere here. This is the radius of curvature. This is the radius of the container, small r. So people generally get confused between smaller and that. And we know this angle is contact angle. This angle is theta. So this angle will be, that is theta 90. This angle is theta. So sometimes they'll ask you find the radius of curvature of the meniscus. It's not small r. R cos theta is equal to small r. So the radius of curvature is actually small r by cos theta. The theta is the contact angle. Now when you have the liquid here, so for a person who is standing here, if you ask him, he will say, I'm inside a air bubble. That is what he will feel. And here the pressure is P naught. And the pressure just below the surface is how much? P naught minus 2s by r. Remember that result? So this person will feel he is in an air bubble and everything is surrounded by water. And the pressure is 2s by r. And let's say this height is h. And here this is a liquid surface. And we know liquid surface here also, the pressure is P naught. So derivation, I'm showing you that this is how the whole thing goes. So P naught minus 2s by r plus rho gh must be equal to P naught. And from here we get h is equal to 2s by rho g capital R. Capital R is nothing but r by cos theta. So that becomes 2s cos theta by rho g r. And that is how we actually derive this. Clear with this? So in this, these are some good ones. I can ask you find the radius of curvature of the meniscus. He's asking capital R, not small r. So here r is the radius of curvature of meniscus. Most people get confused and they write smaller value, so be careful. Yeah, if theta is equal to 0, then both are equal. So now using this logic, right, if you see, so the pressure just here is P naught minus 2s by R2. Pressure here is just below is P naught minus 2s by R1. This is A and this is B. PA is equal to PB because the bottom part is in equilibrium. Like I said, this is too lengthy. Like, I'm just trying to show you the concept. Exam method, don't do all this. You can just directly say, if the surface tension was not there, the heights would have been equal. So whatever extra height you are getting is because of surface tension. So that will be like what 2s cos theta by rho g r1 and this thing, and you just finish it off. So 2s r1. So we get h2 minus h1 is equal to 2s cos theta rho g 1 by r2 by 1 by r1. Clear? And do you guys remember in a capillary action, find the heat produced? When you put a capillary, it actually loses some energy. There is a heat produced. We'll talk about that. It is half of the potential energy. अभी भी एक क्वेश्चन बाकी है ना यहाँ पे. हाँ, time period. How do you find the time period? That's another good question. So what we do for SHM, displace it by small x. So initially this was the height. Displace the liquid by x on one side. Then the liquid will rise here. This will be x and this will be x. So that means total, the restoring force is 2x, isn't it? This weight will be the restoring force. So when you push by x, the difference in height becomes 2x. So F restoring is equal to minus mass into acceleration. So restoring will be rho area 2x into g. The total mass will be rho area, total length is 4L into acceleration. We get A is equal to minus g by 2L into x. That's your omega square. So time period is 2 pi root over 2L by g. Clear with that? So don't forget this. That's an important question even in SHM. Fluid mechanics and SHM. So if you displace by x on one side, the other side will rise by x. The total difference in height becomes 2x. Most people will write that as x, and unfortunately that you will get a 2 missing there, and the whole thing goes for a toss. What about this one? We have a barometer on the Earth's surface. It's showing you 75 centimeters. When you took it to height h, the pressure became P0 by 27, and the height of the barometer is it is showing h at 2r. Find h. So on the Earth's surface, the pressure is P0. The height is 75. When you took it to a height of 2r, the pressure became P0 by 27. So find the height of the liquid in the barometer at 2r from the surface. Gravitation, fluid mechanics. याद है वो G apparent वाला? So I'm mixing up two things. You guys remember barometer? 25, okay. Maybe right. क्या था barometer का formula? Height of a barometer is pressure by rho g. Do you guys remember barometer? Maybe we did discuss few things like let's say if you keep the barometer there, filled with mercury and everything, and we get a vacuum on the top. We had a discussion that what happens if I make a hole here? Yeah. So we did discuss few things. What happens if I make a hole here? What happens if I make a hole here? So there were two different questions like that. Something happened, Rachel.
For B, I was saying.
For B only, something will happen. A is easy, na? If you make a hole at A, the air will enter, this pressure will become P0, liquid will drop. If you make a hole at B, what happens? Ask yourself, okay? At this point, the pressure is P0, and this point, the pressure is zero, vacuum. Means at this point, the pressure inside is P0 minus rho g x, where x is this depth. So pressure inside is less and pressure outside is more. And air flows from high pressure to low pressure, and air bubble will enter inside. You're getting it? You don't get a fountain like this, air bubble will go inside. And this air bubbles will go there and they fill up this space, vacuum goes off and the liquid will come down. So air will start entering inside. So we do have the discussion, check out the notes. So this is P0 by rho g. That's straightforward concept. So initially this was 75 centimeters. So at the new height, pressure became P0 by 27, density remains same, and the gravity became G into 1 plus H by R. H is 2R by R ka whole square. That would be 75 by 27 into 1 plus, how much is this? 9. That's 25 centimeters. Okay with this? What happens if you put a barometer in a satellite? Where the pressure in the satellite is P0 by 2. And you kept the barometer inside the satellite, which is orbiting the Earth. Then what will be the height? Did you get the question? You took this barometer, kept it in a satellite which is orbiting the Earth, and the pressure inside is P0 by 2. Then what will be the height of the barometer? P0 will give you 75 centimeters. It's a good one. I hope you got the question. On the Earth's surface, P0 will give you 75. You took this barometer, kept it in a satellite, right, which is orbiting the Earth, but the pressure inside the satellite is P0 by 2. Now what will be the height? Right there, yeah. कुछ solve नहीं करना है. If you're solving means you're not thinking. मेरे ओम. I confused you by saying there's a P0 by 2. If you didn't say that, maybe you would have guessed it. Nere, Saish. Inside the satellite, what is the G effective? 0. Everything will feel weightlessness. Your entire weight is used to provide the centrifugal, centripetal acceleration, isn't it? So anything that you keep in a satellite will feel as if there is no gravity, means G is 0. Height is infinity, but infinity can't be possible. Means what? The barometer will be full. The liquid will never come down only. Are you getting it? Remember that? So in case of a surface tension, it will be what? It will be full. The entire capillary will be filled. In case of a barometer, that 1 meter will be filled. Liquid will never come down. Are you clear with this? The reason the liquid is coming down is because P0 is pushing up and mg is pulling down. If g is only not there, the atmosphere will push it and the container will be fully filled. Clear with that? So we can add that. So a barometer inside a satellite will always be full. A barometer or a capillary tube. Inside an orbiting satellite. When I said P0 by 2, you guys started thinking. If I didn't say that, you would have guessed it. Inside an orbiting satellite, right, will be full, matlab will be fully filled. Since G effective is 0. Gravity is not there, gravity is there. But all your gravity, you can put it in simple words, the centrifugal force is cancelling gravity. Easy to remember that way. Technically, what is happening? All your weight is actually used to provide the centripetal acceleration. Clear? That is the reason whatever you throw in a satellite inside, you're just floating around. Let's get this. This is a good one. We have a block here, density rho b. Alpha is the coefficient of linear expansion. Cube ka side is L. Rho L is the density of the liquid and gamma liquid. It is dipped inside a liquid. Find x. Find the time period for small oscillations. Find a new x if the temperature changes by delta T. Find a new x if the container accelerates horizontally with A. 4 questions. There, I combined two things, thermal expansion and this. That first one is like a mains level question, like, CET level question. Time period will be a good mains question. C would be a really good one. Mains mate will be on a tougher side. Advanced mate will be an easier one. D is fun. D is also good mains question. Try, get them all. I'll give you 4 minutes. Get first two. I'll give you 2 minutes for that. Then I'll show you the first two. Then I'll give 2 more minutes for the remaining two. That was easy. Hmm. Find x, draw the free body diagram. So this part is immersed in the liquid. You have your own weight mg, which is density of the block, volume, which is L cube into G. The buoyant force, Fb, that will be the weight of the liquid displaced or the volume that is immersed there. So that will be rho liquid, L square, x into G. It is an equilibrium, equate them, you'll get x is equal to rho b by rho L into L. Clear with this? This will actually give the answer for the fourth one also. If the container is accelerating horizontally, if you observe here, this is independent of G. Means it doesn't matter whether the container goes up or down or anything, X will remain same. But what will change is this thing. If you accelerate horizontally with A, then your liquid will become like this. Then the whole system will think this is down. G effective, which is root over A square plus G square. Now your block will actually float like this. This part will still remain X. Answer won't change. Whether you accelerate the container up or down or right or left. Because see now the G is there in both the gravity and this thing, G effective will always cancel out. So the only difference will be the block will get tilted. Clear with that? but that x will remain same. X is the depth of the block inside the liquid. So that doesn't matter whether you accelerate up, down, or horizontal. So that is actually A and D ka question. Let's get B and C. Find the time period for small oscillations and the new x if the temperature changes by delta T. That might be rho B by rho LG. That might be right, Rahman. Let's see. How to get the time period? So initially the block is here. Let's say you push this down by y. So again, we are not interested in the total buy-in force. We are only interested in the change in buy-in force. So this will generate an additional buy-in force delta FB. So actually, if you see the equation, this will be like this: F plus delta FB minus mg is equal to ma. Right? So, but we know F is equal to mg. So this and this will always cancel out. So what you're interested is the restoring force, the additional force which came because of pushing it by y. So what is delta FB? Rho liquid L square y g is equal to minus rho b L cube acceleration. We get A is equal to minus rho L by rho b g by L into y. This is your omega square. So time period is root over L by g rho b by rho L. Clear with this. So when you push it by y further, already you have x, but that will be balanced by mg anyways. So the reason you're oscillating is because of this extra buy-in force. Clear? So that initial F was equal to mg. What is the next one? The temperature thing. Find nu x if the temperature changes by delta T. Again, same story. Draw your free body diagram. Let this be y, the new depth. Now remember, mg will not change. Mg doesn't care about temperature, so this will be still rho block L cube g. Your bind force gets messed up though. Your bind force will be rho liquid, which is rho liquid by 1 plus gamma delta T. The area, now that becomes L square into 1 plus 2 alpha delta T into y into g. Are you getting it? Because the sides will increase. These two are equal. So rho liquid 1 plus gamma delta T. So they can ask a question like this. Find the relation between alpha and gamma so that the depth of that x will never change. That itself is another good question. Most people think alpha is 3, gamma is 3 alpha. No, it is 2 alpha. Rho cube Lg. So we get y is equal to rho b L by rho liquid. G will get cancelled. We get 1 plus gamma delta T by 1 plus 2 alpha delta T. So that's actually your x. X is that initial thing. They can ask question like this. When you increase the temperature, the block sinks more. Then what is the relation between gamma and alpha? So y must be greater than x. So gamma is greater than 2 alpha. It will sink more. If gamma is less than 2 alpha, the block will come out. If gamma is equal to 2 alpha, x will never change. Clear that? That would be a really good question. Find the relation between gamma and alpha if the x does not change. Clear? So you can see with this how many questions you can play. You can play fluid mechanics, you can play SHM, you can play thermal expansion. This is your G effective concept from NLM. So, okay. Take a break, come back by 7:40. Take a 10-minute break, we'll continue from here. Sure, let's get these two. So we have a container fully filled with liquid, density 2 rho. In that there are two spheres. One is the red one has a density rho and the black one has density 3 rho. Tensions are T1, T2. If the container accelerates up, what happens to T1, T2? Increase, decrease remains same. If the containers accelerate horizontally, how will they move? Will they go to the right side? Will they go to the left side? They'll remain at the same place. The second thing, we have a cylinder rotating. Inside we have air bubbles and we have some steel pellets. It's a liquid filled cylinder. And gravity is also there. And if you're rotating with omega, how will these things move? Draw the final positions. Let's get them. These are more theoretical based, but good ones. Increase, decrease, remain same. So something of that sort. Think. I'll give a minute more. These are the kind of questions, which are easy to solve, but little tough. You have to think. Let's see. So if you actually try to calculate the tensions, you will realize for the T1, This will be your bind force, and this is your M1G. So T1 will be the bind force, which is 2 rho Vg minus weight is rho Vg. So tension is rho Vg. If you look at T2, this mg will dominate here, which is 3 rho Vg minus 2 rho Vg. This is also rho Vg. And now when this thing goes up with an acceleration a, G effective becomes G plus a. Both will increase. Both will increase. Are you getting it? It's like, see, I'll tell you the problem here. The previous thing, why x didn't change. For example, let's say if you have 10 and this is 10, okay? If you multiply into 2, will there be any difference? It won't be a difference. But let's say if you have 10 and 9, if you multiply this by 2 and multiply this by 2, the difference also will double, isn't it? If your mg and your bind force are not equal, and if you're messing up G effective, then G effective will actually increase, make the difference bigger. Both the tensions will increase. And if it is accelerating horizontally, then how will the picture look? Now, if it is accelerating horizontally, the G effective will be somewhere in this direction. So this is down. And we know lighter objects will go in the opposite, will go up, and heavier objects will go towards the vertically downward direction. So this guy will actually become like this, the 3 rho. And this guy will actually go like this, the rho. You're getting it? Lighter objects will float, meaning they'll go up. Heavier objects, denser objects will sink. That means they'll be in the direction of G effective. So the same reason, if you actually take a helium balloon, right, and if you put it in a car, when the car goes front, the balloon actually comes in the front. But if you tie a steel ball, the steel ball actually goes backward. So something similar will happen here. So in this figure, the same thing. You can also see this in the washing machine. Kabhi observe kiya? When the washing machine is rotating, the foam comes in the center. The clothes go and stick to the edges. The lighter objects will go opposite to G effective, and denser objects go in the direction of G effective. And here the gravity is also there. So it's rotating, so centrifugal force. So in this thing, you will have your air bubbles will come to this corner. And the steel pellets will come to this corner. Again, what is F net? So this is your centrifugal force, M omega square X, and this is your mg. So for the liquid, this is down. Clear? So air bubbles will go to the left side and this thing into this side. So be careful with that. Which way you will move, it always say like this. Lighter objects or less denser objects will go opposite to G effective. Denser objects will go towards G effective. Getting it? That would be easy to say. Clear with this? Good one, theoretical thing. What about this one? So we have two liquids here, rho and 4 rho, and there is a block of density 2 rho, length L. X is the depth inside the 4 rho liquid. Find X. Find the force on the block due to the rho liquid, and find the buoyancy force due to the rho liquid. I hope you guys remember this statement. Buoyant force due to liquid and force due to liquid are completely two different things. They're not the same. Force due to a liquid is something else. Buoyant force due to liquid is something else. And second one, find the force due to the liquid on the curved surface of the hemisphere. Let's get the first one though. Gravity. Why will gravity cancel out? What do you mean by gravity cancels out? They will sink, right? For the air bubbles, the buoyancy force will dominate.
But sir, on the
There are only two forces,
container,
Purvaja, mg and buoyancy force. That's it. If your mg is greater than buoyant force, you will go in the direction of net force. If your buoyant force is greater, you'll go to the opposite net force.
but there'll also be a pseudo force due to gravity on the container, right?
Pseudo force due to gravity on container. That sentence itself is pretty weird. You need to ask yourself, what are you saying exactly? When do you apply pseudo force? When your observer is in non-inertial frame.
No.
Then what is this m omega square x?
All right.
Okay, the first thing is how much? L by 3, that is easy. The second one is what I'm more interested on. Find the force and the buoyancy force due to the row liquid. No, you'll not talk. See, when you say force due to a liquid, don't talk about buoyant force. When you talk about buoyant force, don't talk about force due to liquid. The force due to liquid comes due to pressure, right? What is buoyancy force exactly? Buoyant force is nothing but the difference in pressure between the lower and the upper surfaces. No, that is what we call as buoyant force. But Archimedes, when he was figuring out this stuff, he didn't have a concept of pressure. You're getting it? So buoyancy force is nothing but the difference in pressure between the lower and the upper surfaces. So the moment you use the word buoyant force, you should not mention pressure anywhere. It's already taken care of. If you want to use the word pressure, don't talk about buoyant force. You can use only any one of them because both are talking about the same thing. Right? Yeah. So let's see. Yeah, that was one of the important discussion we had in fluid mechanics. You should check out the notes. So during Archimedes' time, the concept was not that this guy understood, inherently, like when you put something there, there is a force. He didn't know why that force is coming or what is that force. But later on, we realized that force is nothing but the difference in pressure only. So in this case, if I actually solve this problem using buoyant force, let me show you how we did this also in case you guys forgot. Look at this. I showed this question with both the things. If you solve with buoyant force, you're writing buoyant force and mg. We got an answer. If you want to use pressure, then this block is being pushed by the atmosphere from the outside, and the liquid is pushing from the bottom, and that is balancing weight. And if you observe here, the difference in force at the bottom and the top, this term here is nothing but a buoyant force. Do you guys remember this? So if I ask you this question, what is the buoyant force on the body? The buoyant force on the body is this thing, rho L, L square xg. If I ask you what is the force due to the liquid, the force due to the liquid is this thing. They both are not same. They're completely different things. When I ask you force, it's like if I had to give an analogy, right? It is something like this. Imagine you're doing some charity there. So A gives 100 rupees to B, and B adds 50 rupees, and he donates 150 rupees to charity. If you ask Archimedes, boss, how much did A donate? He will say 100. How much did B donate? He will say 50. If you ask Newton, how much did A donate? He will say 0. I said A didn't give to charity only. Because Newton, FBDs, we always draw the direct forces. We don't take the indirect contributions. He will say B has given 150 to charity. You getting the problem there? So a buoyant force is actually an indirect force. It includes everything, the effect and everything. I'll show you one more example. So how do we solve this though? So let this be inside. This was X. This was L minus X. So I'll take two buoyant forces. If I take buoyant forces, this will be rho L square L minus X into G. This bind force will be 4 rho L square xg. Your own weight mg, which is 2 rho L cube g. Solve this, you'll get x is equal to how much you're getting? 12 by 3. Yeah, L by 3. But now, if I ask you force due to the upper liquid, you just take the pressure at the top, which is P naught plus rho g h into L square. And observe this thing, the bind force is always upward. This is downward. Bind force is always upward. Now, the thing comes like this. Technically speaking, rho is actually pushing you down. But what Archimedes argues was this. He will say, okay, what if rho didn't exist? If rho didn't exist, the pressure at the bottom would have decreased. If the pressure at the bottom is decreased, right, then the force from the bottom will be gone. So indirectly, what this rho is doing here, this rho is increasing the pressure at the bottom, and that pressure is pushing it up. So it is indirectly contributing for the floating of the block. And that indirect contribution is this quantity, the bind force. Are you clear with this? It's like I gave you 100 rupees, you added 50 rupees, and you gave 150 rupees to the charity. I contributed 100, right? But I didn't submit it directly. Are you getting it? So Newton will say, boss, if you didn't give to the charity directly, then you didn't give. But Archimedes will say, it's not like that. You actually contributed 100, but you didn't give it directly. Clear with this? So whenever someone asks you find the force, we always take care of the direct forces. It's like asking this question. I keep 2 blocks. This is 2m and m. What is the force of m on the ground? 0. There is no force between m and ground. But inherently, you can feel it, right? It is actually giving mg value, right? So that's it. That's the only difference there. So if I had to ask you one more question on this, suppose let's say we have 3 liquids. Let's say the site is H1, rho 1, H2, rho 2, H3, rho 3. And let's say you keep a cylinder like this. Cylinder area is A. Now, if I ask you, find the bind force due to each liquid and find the force due to each liquid. Can you get them? Liquid 1, liquid 2, liquid 3. Do you guys remember we had something like this in EMI? Faraday's law and motional EMF. They're not two different things. Faraday's law is completely experimental. Faraday didn't know why you are getting a potential difference. Motional EMF is morely theoretical thing. But both are talking about the same thing. So when a rod is moving, you should not say like, oh, there's a motional EMF and there's also Faraday's law. Use one of them. You can't use both. What's the liquid 1 ka bind force? Rho 3 and rho 1 area H1 G. Rho 2, only this part is H3, yeah? Not the whole thing. Rho 2 A H2 G. Rho 3 A H3 G. That was easy. But if I ask you force due to the liquid, 0, 0. Why 0? Look at the free body diagram. The green is pushing this way, right? They'll all cancel out. The green is not exerting any force on the cylinder. 0. The red also, right, will cancel out. They are also not exerting any force on the cylinder. So according to Newton, green and red are not doing anything. Now if you look at this one, then this will be P naught plus rho 1 GH1. Rho 1 actually is increasing the pressure. Even though it's not doing indirectly, it is actually contributing. Rho 2 GH2, the pressure increased, plus rho 3 GH3 into area. This is the force due to the third liquid. Are you getting the argument? If rho 1 and rho 2 had not existed, the pressure at the bottom would have decreased and the whole force would have decreased. So be careful with this thing. Force due to a liquid and the bind force are completely different things. Clear? Now, how to do the second one though? You can draw the free body diagram. Now you can see, I can do the same argument there. So the liquid is being pushed from the top. How much is that? P naught plus rho gr into area. And the liquid is also pushing from the surface. So can I argue like this? So buoyancy force is nothing but the force on the lower surface minus force on the upper surface. Isn't it? The difference in pressure at the lower and the bottom will generate the buoyant force. And you know buoyant force, which is rho liquid, 2 by 3 pi r cube g. This is the force on the curve. And this will be P naught plus rho gr into pi r square. There you'll get the answer. Easy? Any doubts on that? Same question if I play like this. Instead of this, what if I keep it reverse? Now if I ask you find the force on the curved surface, then what will you say? Means I am asking you force on this guy. You can't use projected area. P is not constant. If P is constant, you could have simply said P into rho g, that is surface area, but you can't do that here. Right, Ahana, something of that sort. Think, I'll give 30-40 seconds and I'll tell you something. Like I said, if you actually figured it out, it won't take much time to solve. The figuring part is the headache. See, can I argue like this? What is this curved surface exactly doing? Can I say the whole weight on top of the cylinder, if I take this part, the water, and if I draw only that FBD, the force on the curved surface must be equal to force on this surface, isn't it? And that must balance the weight on top of it, na? Is that clear, everyone? So all that water on top of that curved surface must be balanced by whom? This curved surface only. Clear? Done. You can find that thing. How do you find that? So this total height is r. So the F curve will be density of the liquid, volume will be cylinder, it is pi r square into r minus 2 by 3 pi r cube into g. Bus. Not only this shape, you take any weird shape, if you put any weird shape, so the force acting on top, the curved surface must be this total weight which is on top of it. Is that making sense? So instead of doing all integration and everything, you can just argue with this statement that curved surface must be balancing the weight of the water on top of it. Because if you draw the FBD of the water on top of the curved surface, there is no one else to balance other than the curved force. Are you clear with that? Got it? So there, that is how we do it. If it is this way, I'll use bind force. If it is this way, I'll take the weight on top of it. So it's a pretty good one. So then you can ask a really good advanced question. If I put a full sphere and tie it here, and I can ask you, find the force between the upper hemisphere and the lower hemisphere. There will be some tension in the middle, right? So find the force between upper and the lower hemisphere. Now you can combine both and you can play around. But now that's a little going beyond. We can see later on. Let's get this. We have a rod tied on one side. The density of the rod is rho and liquid is 3 rho. Length is L. Some part is floating out and some part is sinking inside. Find X. You guys should definitely try all these questions again. And whatever questions you didn't get or had a confusion, you should do them again. Same story. Draw the free body diagram. So if you draw your FBD, there's an important concept here. Where does your gravity act? Gravity acts on the center of mass. Where does the bind force act? The bind force acts on the center of mass of the displaced liquid. Clear with that part? Right? Center of mass, right? Or the bind force will act on the center of mass of the displaced liquid. Meaning if you take this as X, so we can call it center of bind force, FB, that will act at X by 2. That is an important concept in this. Clear with this? So be careful with that. Center of mass and the bind force will act at that point. It will not act at the center of mass of the rod. And then what is FB? That will be rho liquid, area, XG. Mg will be rho body, ALG. You can take torque about this point, right? And you can take this angle to be theta. That will be mgl sine theta, mgl by 2 sine theta is equal to bind force. That distance will be L minus x by 2 sine theta. Solve this, you'll get an answer from here. I'll leave it to you. That is the main idea there. The bind force should be acting on the center of bind force, the center of the displaced liquid. Clear with this? Let's get these two. Standard question. We have an ice block, 0.9 gram per cc. We have a salt water, 1.05 gram per cc. If the ice melts, what happens to the water level? What is Reynolds number for streamline flow, viscosity and density? Should they be big or small? Bernoulli's equation is valid for what? I think options would be something like this. Bernoulli's equation is valid for any two points in a liquid. Bernoulli's equation is valid for two different streamlines. Bernoulli's valid is equal for 2 points on a streamline. Bernoulli's valid is equal to something like that. So frame questions of that sort. So here you have to be careful. When ice melts, what kind of water you get? You get fresh water, which is 1 gram per cc. You don't get salt water. So first of all, ask yourself, normally what would have been the depth? So when you remove that ice block here, the cavity which you get x, if you remember the formula, x was rho b by rho l into L, right? This would be less than 0.9 L, isn't it? No, greater than 0.9 L, less than 0.9 L, isn't it? So that cavity ka volume is less than 0.9 L cube. But when your ice melts, how much water you get? If this volume is V, we get 0.9 V, isn't it? So what will happen? So if you remove the ice block, the cavity ka volume is less than 0.9 L cube, but when it is melting, and if you take this water now, and if you pour it back into this cavity, won't it overflow? Right, so increases. Check out the class notes. We did for 3 cases. Rho less than 0.9, greater than 0.9, that less than 1, greater than 1, and equal to 1. Reynolds number का formula याद है? Rho VD by eta. D is the diameter of the pipe. For a streamline flow, Reynolds number must be less than 2000. More than 3000, it will be steady, unsteady flow or turbulent flow. Between 2000 to 3000, we don't know. So the lesser the Reynolds number, the better the streamline flow. So you can see viscosity is in the denominator. So viscosity should be high. Density in the numerator, density should be low. So liquids which have high density, low density and high viscosity will go in a streamline flow. What is Bernoulli's equation? It is valid for 2 points on a streamline. It's not even valid for 2 different streamlines. But then again, we make a statement saying, the streamlines are identical at a point. So we just take any 2 points. But theoretically, it is valid only for 2 points on a streamline. Hope you remember what is Bernoulli's equation. P naught plus P plus rho GH plus rho V square is equal to constant. Anyone remembers what is rho GH called? There's a name for this thing. They call it pressure head. That is work done by pressure per unit volume. Rho GH is potential energy per unit volume. It's potential energy head. This is called kinetic energy head. This can be asked in units and dimensions. Kinetic energy per unit volume. If you actually multiply in all this thing, you'll actually get work energy theorem. This is pressure head, so that's work done by pressure unit volume. This is potential energy head. It looks like pressure, but these are actually energies per unit volume. Let's get this thing. I hope you remember velocity of flux. There's a general solution I gave you. I mixed up everything in this one question. Look at the question. We have a container which is sealed. The pressure is 3P naught. There is a block here. There is a piston. There is a liquid row. There is a liquid 2 row. And there is a small hole. Find the speed of the liquid coming out. Generally in exam, they'll put 1 or 2 things maximum. Here I just dumped every case. let's see if you remember that velocity of flux ka general equation which I gave you one result. Aeroplane wing, find the thrust force on the wing. You remember what effect that is called? When the ball drifts, there's a name for it. CET mein they'll ask. Magnus effect. Yeah. Forgot the formula. Velocity of flux is given by root over 2 delta P by rho. This is the rho liquid coming out. Delta P is the pressure just inside and just outside. Difference pressure inside and outside hole. You should check out the note. We did this. So then what is the pressure here? This is 3P naught. This is mg by area. So delta P will be 3P naught. Then the block will generate a pressure of mg by area. Then that liquid will generate rho GH. The second liquid will generate 2 rho G2H. This is the pressure inside the hole and outside is P naught. And the rho liquid which is coming out is 2 rho. Substitute there, will get the answer. Clear with this? What about thrust force here? The thrust force will be the differential pressure P1 minus P2 into area. We can neglect the height of the wing. Then we use Bernoulli's equation P1 plus half rho V1 square, P2 plus half rho V2 square. So P2 minus P1 will be half rho. That is the density of air minus V1 square minus V2 square into area of the wing. If they ask you on the aeroplane, general aeroplane will have 2 wings, so into 2. Don't forget that. One time they played a game like that. They said area of one wing, they gave 500 meters square, 500 something. And they said find the force on the aeroplane. And there were 2 answers. One answer was like 1,000 and one answer was 2,000. Answer was 2,000. And the argument was there will be 2 wings, right? And they gave only area for one wing. Matlab, you know how to do, but still you go for what to do. Unfortunately, sometimes it happens. You have to be careful. Next thing, if you have a ball, you gave V and omega in atmosphere. What is the path of the ball? Neglect gravity. Second is a good question. You have a container fully filled, small hole. Find the ratio of time taken to empty the upper half and the lower half. This is a very important result. Should definitely mug up. Exam mein time nahi milega to derive this. Where x is the height of the liquid as function of time. So first one, what will happen? It will fly. So here the speed will be V plus R omega. Here the speed will be V minus R omega. So here it is P1 and here it is P2. And we know the equation P plus half rho V square is constant. If you have more velocity, you'll have less pressure. So P1 is greater than P2. So the ball will get an upward thrust. So it will start going up. Second is a really good one. This itself is a mains level question, like find the time when the tank becomes empty, when x is 0, where x is the height of the liquid at time t. You should definitely go and check out the derivation. Mains may you won't have an issue, but advanced may they'll frame like this. They will say instead of a container, we have a spherical shell and we have a small hole. Find the time taken for the shell to become empty. So then you need the derivation. Mains may I don't think they'll touch that, but the result is important. P2 will be more velocity, less pressure, na? Second one, I think Aditya got the answer. Find the time taken, ratio of time taken for the upper half and the second half to get empty. Root to नेरे आना. So let's find the total time to take empty, okay? Total time t will be root 2h by g, a by a. For the first half, that is 0 to h by 2, then this guy will be root over h by 2 is equal to root h minus a by a root g by 2. I'll just call it t1. So from here I get t1 ka value. Root h minus root h by 2 by all that a by u root g by 2. And what about the second half? T2 will be t minus t2, isn't it? Take the total time and subtract the upper half. And you're asking upper half and the lower half, so divide t1 by t2. The denominator will anyway go off. You get root h by 2 by this will be a root h minus root h minus root h by 2. Root this thing also goes off. You end up with 1 minus 1 by root 2 by 1 by root 2. Root 2 minus 1. Or you could have done this way also. T2 ke liye na, you will take the, what is h there? Initial height of the container, right? For the second half, you will take h is h by 2 and x is 0. That also works, meaning you are assuming the water container is half filled and from there it started to leak. But that's a pretty good important result, right? Definitely remember this root x is equal to root h, a by a, g by 2. This is only for small holes. For big holes, anyway, they won't ask you that because nahi kar payenge. What about this guy? Top view. The liquid is entering with V and the area in the middle suddenly becomes a by 2. Find the direction of the force and the torque on the pipe. Which way will the pipe move and which way will the pipe rotate? Option should be like this. It will try to go towards the east, clockwise, west, anti-clockwise, north, northeast, southeast, clockwise. So two questions. Which way will it move and which way will it try to rotate? Let's see. One thing is clear. This guy will come out with a speed at 2v. And we know force due to a water jet is rho a v square. So when this water is entering here, it will push here with rho a v square. And the water is leaving here, it will also push backward rho a v square. You're getting, when it is taking a turn, it will actually push back also, right? Third law. And here, when it is entering here, this will become rho. Area became a by 2, but the speed became double. So this actually becomes 2 rho a v square. Force increases, and this will push again here with 2 rho a v square. So you can clearly see this way and this way, this guy is dominating, isn't it? If I take this as f, this will be f root 2. So the body will go southwest, and the rotation would be in this direction, which is clockwise. Clear with this? The pipe will have a tendency to move that way and rotate this way. It might not move, you will put clamps and everything normally, but it has a tendency to do that way. Clear? F root 2 will dominate. So when the pipe becomes thinner, area becomes half, but velocity becomes double. The force becomes double. Clear with that? Let's get these two. So we have a cube here. On the right side, you made a circular hole. On the left side, you made a square hole. Radius is a, side is a. Find the distance y by x, the depth, so that initially container is at rest. Second thing, you took a container, a small hole on a smooth floor, height is h. Find the initial acceleration of the container. So when the liquid comes out, it acts like a thrust force. So the container will try to slide. Find the initial acceleration. That was easy. Same story. So if the water jet is coming out, it will exert a force F1, which is a rho. Area will be pi a square, and the speed will be root 2 gx ka square. Remember, force ka formula is rho, area v square. This force will be F2, which is rho. It's a square plate, so a square and root 2 gy ka whole square. Since it is not moving, so F1 is equal to F2. Same thing here, water will go with V, so it will exert a force F. F is equal to mass into acceleration, and force will be rho, area of the hole A, V square, which is root 2 g h ka square. Mass will be rho, capital A, h into acceleration. You actually get something interesting here. This rho and h actually goes off. You end up with A by A 2g. You actually get a constant acceleration. It actually doesn't depend on the height. If you can make the container, make the liquid always horizontal somehow by putting a piston on the top, the whole container will always go with a constant acceleration. Clear with this? Let's see one more before going ahead. This is a good one. I hope you remember. Let's say the velocity of a liquid particles is given by same question from the class notes. I am giving it. It's a good one. So minus b by j cap. Can you draw the streamlines? This is the velocity of the particles on a streamline. A and B are constants. Find the equation of streamlines. You guys remember the definition of a streamline? Streamline is the path of the particles in which, this particles move. Again, what is a particle in a liquid? It's a collection of molecules. So on a streamline, the speed at a given point is constant. It doesn't change with time. You guys remember the theory for this? In case you forgot. There, see. Equation of a streamline. So when you take the slope of the streamline, right, tan theta is Vy by Vx. So dy by dx is Vy by Vx. So Vy is the vertical component and Vx is the horizontal component. So this was the same question there. The slope is given by dy by dx. So that is Vy by Vx. So put that and integrate, you'll end up with this, which is actually a hyperbola. C ka value can be anything. When you try to plot the graph, this is how it looks. But different values of C, you get different lines. So the liquid is starting on the y-axis and it is getting converging on the x-axis at infinity. This is how the streamlines will look. This is the main thing, everyone. Right? In case you forgot, you should definitely check this out. So we get dy by dx is equal to minus by a plus bx. You integrate this, you end up with c by a plus bx, something of this sort. So it's your equation of the streamline. So for different values of this, this is how the streamlines should look at that. I gave you one more example in this. There, if the equation was 1 by x and 1 minus y, the streamlines will be actually circular. You can play around with the equation. Check this out, equation of a streamline, it's a good one. Okay, we'll take a break. Then we'll catch up at again 9 o'clock, right? So go have your dinner and everything, and we'll start the speed test at 9. So any doubts, anything else, you can stay back, or else you free to leave, disconnect. You can rejoin again at 9.
Yes, sir.